Alright kiddos, welcome back, and today we're going to discuss something called hydrolysis as it pertains to this unit on acids and bases. Now, sometimes the concept of hydrolysis is hard for students to understand. I'm going to try to simplify it for you kiddos. Simply states that some salts, when dissolved in water, can affect the pH of the water solution. Now quickly, a salt is simply a generic term for an ionic compound. We have a positive ion that's electrostatically attracted to a negative ion. And when placed in water, those two ions can dissociate or separate from each other. When that happens, they have the potential, sometimes, of reacting with water molecules and tearing it apart. Now, as we go through this, try to imagine a water molecule, H2O, as an H plus bonded to an OH minus. That will help us understand hydrolysis, I hope, a bit more simply. So think of water as H plus stuck to OH minus. Now, hydrolysis, the definition of it is simply that some salts can react with water to produce either hydrogen ions or hydroxide ions in solution. So in other words, some salts, when we place them in water, can cause my water to become acidic or basic, depending upon how they tear up the water molecule. Now, for you to completely understand this, I'm going to ask you again to memorize your strong acids and strong bases. A couple of weeks ago, for a different part of this unit, I asked you to learn your strong acids and bases. Many of you, it's my guess, haven't done so yet. So please learn your strong acids and bases. They're listed here in your notes again. I'm going to put a little star by them again. Your strong acids are hydrochloric, hydrobromic, hydriodic, sulfuric, nitric, and perchloric. Your strong bases are the group 1 hydroxides, which include, of course, lithium hydroxide, sodium hydroxide, potassium hydroxide, and so on, along with barium hydroxide, strontium hydroxide, and we're going to include calcium hydroxide. Now, the reason I'm having you learn those or memorize those is because strong acids and strong bases, when placed in water, separate from each other 100% of the time. So for instance, if I had HNO3 placed in a water solution, 100% of the time it would dissociate into H pluses and NO3 negatives. It would actually ionize and form those two ions all the time. These two ions are not attracted to each other when placed in a water solution. They're more attracted to water than they are to each other. Now, the same thing happens with strong bases. Let's say I had a strong base, lithium hydroxide, and I placed that in water. Those two ions are more attracted to the water molecule than they are to each other. So they separate into lithium and hydroxide ions 100% of the time. These two ions are not attracted to each other. So try to remember that as we discuss hydrolysis. Now, there are some salts when we place them in water that will not react with water to produce hydrogen or hydroxide ions. These are salts that come from strong acids and strong bases. What does that mean? They come from strong acids and strong bases. Well, let me give you a classic example. NaCl. Doesn't sodium come from one of your strong bases? And doesn't chloride come from one of your strong acids? Now, when I place sodium chloride in water, they dissociate to produce sodium ions and chloride ions. Now let's explore to see if they are attracted to either part of my water molecule. Now remember, when you do these, we need to think of water as H pluses bonded to OH minuses. So think about this. Will Na plus from sodium chloride be attracted to the negative part of water molecule? Well, Na pluses and OH minuses stick together when I put them in water. Of course they won't. Na plus will not form OH minus in water. This does not happen. So there's no reaction here between the sodium ions and the hydroxides. Let's take a look at the chlorides. Will the chlorides be attracted to the H plus part of the water molecule? Does HCl exist as a molecule stuck together in water? Well, no, of course it doesn't. HCl does not exist as a molecule in water. They ionize 100% of the time when placed in water, so that will not react with the water molecule. So since Na plus and Cl minus do not react with water, we would say that this would be a neutral salt, and the pH of that solution would be 7. Now, what about salts that produce basic solutions? These have ions that come from negative ions of weak acids. So you'll notice that those salts will have negative ions that come from weak acids. Let's give a great example here. Instead of NaCl, let's work with NaF. Okay, now we already know that Na plus, when I throw that in water, will not react with the water molecules. NaOH does not exist as a molecule in water. However, what about the F negative part of sodium fluoride? Will that react with water? Well, let's see. Once again, if we look at water as H pluses bonded to OH minuses, will this F negative react with the positive part of water and produce HF? In other words, do HFs like to stick together? They do, don't they? HF, hydrofluoric acid, is a weak acid. It's a weak acid because these two ions, H plus and F negative, are more attracted to each other than the H plus is attracted to the hydroxide in water. So the molecule HF will form in water. It will steal the H plus away from the water molecule, leaving you with a hydroxide all by its lonesome. Now, since you produced a hydroxide, this would be a basic solution, and the pH would be greater than 7. All right, what about salts that produce acidic solutions? I'll bet you already know where their ions come from. Think about it. Salts that produce acidic solutions have ions that come from positive ions of weak bases. Let me show you why. Let's use zinc chloride here, ZnCl2. So when ZnCl2 is placed in water, it forms Zn2 plus ions and Cl negative ions, right? Well, let's see if either of these will react with the water molecule. Once again, think of water as H plus bonded to OH minuses. Now, we already know about the Cl negative. Will the Cl negative react with the positive part of the water molecule to form HCl? No, HCl is a strong acid. It ionizes 100% of the time in water. HCl's do not stick together. What about the Zn2 plus? That's not one of your strong bases, is it? So doesn't that mean that the Zn2 plus will be attracted to the negative part of the water molecule, and you will form ZnOH1 plus. Remember, it was 2 plus. And it pulled apart the hydroxide, OH negative, from your water molecule. So now it's ZnOH1 plus. Now, since we pulled the OH minus away from water, we have an H plus left over, all by its lonesome. We have produced hydrogen ions in water from that salt. So this would be an acidic solution, and the pH would be less than 7. Now, in a bit, we're going to talk about what happens when both the positive ion, the cation, and the negative ion, the anion, both tear water apart. For instance, NH4F. Think about that for just a moment. What if NH4F were placed in a water solution? All right, well, let's try it. NH4 pluses and F negatives. Let's see if these guys will react with water. Remember, think of water as H plus bonded to OH minus. So will NH4 plus be attracted to the OH negative part of water? Yeah, it will. NH4OH is a weak base, and they love to stick together. So when I do that, I will form NH4OHs, and I will have H pluses left over in my water solution. I will have made hydrogen ions and made that solution acidic. But wait a minute, I also have F negatives in my water. Well, F negatives react with the positive part of the water molecule to form HF. Yeah, HF is not one of your strong acids. It's a weak acid. So HF molecules do exist in water. And we'll have the hydroxides all by themselves in water. So one part of this salt produces hydrogen ions. The other produces hydroxide ions. Who wins? Is it neutral? Well, when we end up with a situation like this, we need to look up the equilibrium constants for the two reactions. Turns out the Ka, the equilibrium constant for ammonium ions, is 5.6 times 10 to the negative 10th. The Kb, the part that would make this basic, for F negatives is 1.4 times 10 to the negative 11th. Which one's bigger? That's right, the Ka is bigger. So since the Ka is greater than the Kb, we would have, that means therefore, an acidic solution, and the pH would be lower than 7. Okay? All right. Let's work a bunch of examples here. Hopefully by the time we finish example 9, any confusion you might have will be sort of put behind us. So let's give it a whirl. Remember, when we do these, folks, pretend that water is H pluses bonded to OH minuses. And we have to see if these positive ions or negative ions are strong enough to tear the water molecule apart. Now, we already did letter A earlier, but we'll do it again just for fun. NaCl has Na pluses and Cl minuses when I place them in water. So we have to decide if Na plus or Cl minus can tear the water molecule apart. So, does Na plus come from a weak base? Is it strong enough to yank out that OH minus from water to form the molecule NaOH? Nope, NaOH as a molecule does not exist in water. It's a strong base. Na plus and OH minus separate 100% of the time when we place them in water. So the Na plus will not react with the water molecule. Well, chlorides react with the positive part of the water molecule to form HCl. Does molecular HCl exist in water? No, HCl is a strong acid. They ionize 100% of the time when placed in water. So those will not react with your water. So since neither of these will, we would say that this would be a neutral salt and the pH would be equal to 7. All right, let's switch colors for the next one so we don't get confused. Potassium acetate. We have K pluses and C2H3O2 negatives. Well, either of these have the ability to tear apart the water molecule. All right, remember, think about water as H plus bonded to OH minuses. Well, K plus react with the OH negative part of water to form the molecule KOH. No, it will not. KOH is a strong base, and they separate, dissociate 100% of the time when placed in water. What about the acetates? will C2H3O2 negative react with the positive part of the water molecule to form the molecule HC2H3O2? Yeah, it does. HC2H3O2 is not one of your strong acids, so it's weak. So that means it exists as a molecule in water. Well, if I pull that H plus away from my water molecule, don't I have hydroxides all alone now? I do. So this solution would be basic and the pH would be greater than 7. Alrighty, let's try NaF. That's another one we did just a few minutes ago. Why don't you try doing it, Na pluses and F negatives, without my help and without looking back on the previous page of your notes. So write the applicable reactions and then decide whether this is acidic, basic, or neutral. And then come back to the video and we'll see how you did. Alright, welcome back. Boy, we've seen Na plus in water lots now. Hopefully you know that that will not react with water. NaOH does not exist as a molecule in water. It's a strong base. However, F negative will form HF molecules in water. HFs like to stick to each other. They're weak acids. So, if I think of water as H pluses bonded to OH minuses, and the F negative just pulled out the H plus from water, don't I have OH negatives left over? I do. And so since I have OH negatives left over, this is also basic, and the pH would be greater than 7. All right, try the next one. NH4Cl. In NH4Cl, kiddos, we have NH4 ions, ammonium ions, and chloride ions. I'll give you a minute to do that. Come back to the video and see how you did. All right, welcome back. NH4 plus. Will that react with, let's see, we have H plus and OH minus. Will that react with the H plus part of water? No, because that's positive and that's positive. They'll bounce right off of each other. Will it react with the OH negative part of water to form NH4OH? NH4OH is not one of my strong bases, so that will stick together in water. So if I pull the OH minus away from water, don't I have H pluses left over? I do. So what about the Cl negatives? Does HCl exist in water? No, it does not, so that's not a reaction. So this salt, since I produce hydrogen ions, will be acidic, and the pH will be less than 7. All right, do the next two without my help. Come back to the video, folks, and see how you do. Now, honestly, try these by yourself first, and then come back to the video to see if you're getting these. All right, welcome back. AlCl3. Let's see, we have Al3 pluses and Cl negatives in water. Well, I'm just going to do the Cl negative first because we beat that to death. That will not react with water, will it? HCl does not exist as a molecule in water. However, Al3 plus, let's see, H plus and OH negative. Will the Al3 plus react with the hydroxides? Yeah, AlOH2 plus will form. It was 3 plus. It's going to react with your OH minus and become AlOH2 plus. So it's going to rip away the hydroxide from the water molecule and leave you with hydrogen ions. Now, since you have hydrogen ions being created, this would be acidic, and the pH is less than 7. And then finally, your last one, let's go with KNO3. So we have K pluses and NO3 minuses reacting with water, or maybe not reacting with water. Let's see. H plus and OH minus. Will the K plus part of this react with the OH negative part of water and form KOH? Do KOH molecules exist in water? No, they do not, because KOH is one of your strong bases, and they get torn apart by water 100% of the time. How about nitrates? Will the NO3 negative part of water react with the H plus? Or the NO3 negative part of this salt react with the H plus of water to form HNO3? No, it will not, because HNO3 is one of your strong acids, and HNO3 will dissociate 100% of the time when placed in water. So since neither of these react, this solution would be neutral, and the pH would be 7. Okay, now in class next time we're going to do a bunch of these. So please go through this again. Make sure you guys have an idea as to what acidic salts are, what basic salts are, and of course what neutral salts are. All right, see you soon, kiddos. Bye-bye.